Well, greetings everyone, and welcome to our Boston Digital Business Leadership live event. This event is being produced by the Digital Business Institute and by the Information System Department at the Questrom Business School at Boston University. Our Digital Business Institute is a vibrant digital hub featuring research and thought leadership produced by faculty, administrators, and many of our alumni. Here we'll bring theory to life and apply it to exciting challenges facing leaders in business and in higher education. I'm Professor Avi Seidman from the Questrom School of Business at Boston University, and I'll be moderating this exciting live event today. Today's topic is, can machine learning improve human decision-making? In other words, we are going to be looking at AI as a complement rather than as a substitute for the human operator. I'm joined today by our distinguished guest speaker, Professor Hamza Bastani. Professor Bastani is on the Faculty of Operations, Information and Decisions at the Wharton School of Business in the University of Pennsylvania. She started her academic career here, not far from here in Boston at Harvard University, where she graduated summa cum laude in physics and mathematics. Later, Hamza moved to the West Coast to Stanford University, where she got a PhD in electrical engineering just 4 years ago. I met Hamza as a doctoral student at Stanford while I was visiting there for conducting some joint research projects. She impressed me immediately with her creative curiosity and with her mathematical thinking. Despite her young academic age, Professor Bastani has already published 8 scientific papers. Almost all of them got into our top-level journals, and she won 10 scholarly prizes, including the first place in the Piscala Award for the best paper in healthcare. One she won in 2016 and another one in 2019. And she won the first place at the EMSOM student paper competition in 2020. And the list goes on, I'll skip the rest. She's now working on a lot of exciting topics, including interpreting predictive model for human-in-the-loop analytics and on the analysis of Medicare pay-for-performance contracts. So Hamza picked some very interesting, thought-provoking topics. And Hamza, the stage is yours. Let us plan to go till about 1:50 p.m. So we leave around 10 minutes for audience Q&A. But let me start with the personal curiosity question that I didn't have a chance to ask you before the seminar. Basically, where did your interest in AI and operations came from?
Thanks, Avi. That was a very kind and undeserved introduction for me, but I also have very fond memories of meeting you at Stanford. It was great. AI and operations, I think I came from, like you said, I came from a sort of non-traditional background. I didn't study operations, so I actually came in with more of an interest in AI. I think there's been a lot of progress in developing the main thrusts of AI, but there's a lot of interest now in actually integrating AI plus X. So there are a lot of domain-specific challenges that AI doesn't necessarily solve, or like the machine learning literature hasn't necessarily considered. And I was personally drawn to healthcare operations, and now I'm very interested in sustainability and social good. And I think there are a lot of domain-specific issues, like I mentioned, that involve new algorithmic techniques, which I find very exciting, because then you can take the nice theory that people have built up in computer science and try to translate it to practice.
Okay, go ahead.
Thank you everyone for having me here. I'm excited to talk to you guys about some work I've been doing with Osman Bastani at UPenn Computer Science and Park Sanchesri, who is a PhD student at Wharton, but has just accepted a faculty position at UC Berkeley Haas in the fall. So the main motivation AI can complement and speed up human learning. So we all know that human learning can be costly. So there are a couple statistics saying that if someone is newly recruited on the job, it can take them several years to become fully productive. Worker training is pretty expensive. And that's all in kind of a static environment. But I think even more interestingly, whenever there are new technological disruptions, that makes training humans even harder, because then they have to unlearn old strategies and adapt to the new environment. So just as an example, when surgeons get presented with new surgical devices, the duration of surgery can go up by about a third, which obviously harms their productivity, it harms patient outcomes, and so on. So we want to understand how we can speed up learning. One of the things that we learn from organizational behavior literature is that people can learn effectively from other human peers who are experts. So for example, there was a study conducted in the emergency department where some physicians are much better at quickly turning over patients than other physicians. This is typically because they're more forward-looking. Maybe they ordered labs in advance, knowing that there's going to be a bottleneck. So maybe they anticipate those things faster, and so they're able to more quickly get the patients out of the room so that they can treat the next patient. And if they actually publicly report these performances, they found that they were actually able to communicate best practices with each other, what we in this talk will call tips, so that other physicians who are maybe slower were actually able to improve their productivity by about 11% in a pretty short time frame. So knowledge transfer is clearly a promising solution. But in a lot of settings, knowledge transfer is difficult. So if you're thinking about maybe the gig economy or drivers on Uber or Lyft platform, it's not like they know each other and can effectively communicate best practices. Some of them are going to be better at things like fuel consumption or revenue maximization, but that's not necessarily easily going to be transferred to other drivers who are maybe new to the platform. So we wanted to understand whether AI or machine learning can help facilitate this knowledge transfer. And one promising source of data that I believe is largely untapped is trace data. So in a lot of these domains, like if you're thinking about Uber or Lyft, every driver action is actually recorded on the platform in real time. Similarly, if you're a physician and you look at Epic or some of these electronic medical records, every single action is recorded on there, like when a physician looks at a chart, when they order every lab, and when they perform every procedure, along with the timestamps. This data is almost a little bit too granular to immediately be useful. It's a very, very large volume. It's very noisy. And so it's difficult for humans to kind of look at the data and get any kind of meaningful insights into why some people perform better than others. But this is exactly the kind of task that you might imagine machine learning would be able to sort out and extract some useful and meaningful insights. And that's exactly what we're going to try to do here. So in this work, we're taking this kind of high volume, noisy trace data, and then we're applying kind of state-of-the-art machine learning techniques to extract some best practices. These best practices, it's very important that because we're going to present them to actual humans, they need to be interpretable and they need to be phrased in a way that people will actually comply with them and will actually be able to improve their performance using them. So we're going to do a little bit of new algorithms on the interpretable machine learning side. And then we're actually going to do a behavioral experiment where our randomized control trial, where we have a simple kitchen game where we're going to present them different kinds of tips or best practices that we've gained through our algorithm as well as other algorithms. And we'll see whether or not we're actually able to improve human performance. Okay, so if we're thinking about actually improving human performance, there's the algorithmic side about how we actually extract these tips. But there are a couple of issues we should keep in mind, which I'll circle to towards the end, which is that just because you give someone a tip doesn't mean that they're going to comply with it, especially if it's from an algorithm. There's something called algorithmic aversion, where people might not trust the tip. Importantly, there's also interpretability issues. So even if someone does trust the tip, if they don't really know how to incorporate it into their current workflow or their decision-making process, we might not actually be able to improve performance. And similar, there's also a learning curve. So sometimes there are negative spillovers from taking on your tip. Maybe they'll change another good behavior that they were already doing to accommodate the tip, or maybe they'll take on new good behaviors. So for all of these reasons, it's important to kind of study how these tips will affect performance in a sort of controlled environment where we can see how people adapt their policies. And because of this, we're going to start off by doing a case study in a simple queuing game that we designed for Mechanical Turk participants. So this is a very simple game that's kind of inspired by this popular video game called Overcooked. So participants are basically tasked with managing a kitchen where they need to make 4 burgers and within a pre-specified amount of time. And the faster they make the burgers, the more points they get and the more money they'll be paid in the experiment. So making a burger involves 3 simple sequential tasks. They have to be done in sequence, but you can make the burgers concurrently. So you need to chop the meat, cook the burger, and plate it so that you can serve it. And ticks here are like a unit of time. So 2 ticks will mean that this is a much faster task than cooking the burger, which is clearly the bottleneck in this particular operation. And the Amazon Mechanical Turk participant will have access to 3 workers that they can deploy to actually conduct this task. So we have a chef, a sous chef, and a server. And they're told that these people have kind of heterogeneous skills. So they need to think about what is the optimal matching of tasks to assign these people. But they're not told what exactly those skills are, but they can quickly learn them. So I'll tell you guys, the chef, if for example, is very good at chopping and cooking, but really bad at plating. The server is the exact opposite, whereas your sous chef is kind of like an average Joe who does all tasks like relatively well across the board. So now if you know this, an optimal solution will try to match the chef to the task that they're good at, the server to the task that he's good at, while keeping into account that, bottlenecks will arise and trying to avoid those bottlenecks. So this is roughly how the experiment proceeds. So whenever we get a task, so at any point of time, they can be working on 3 dishes. So they're out of the 4 total burgers. So let's say I want to assign chopping the first burger to the chef. Now my sous chef can't cook the next burger because the chopping needs to be done first. So maybe I'll assign chopping the second burger to the sous chef and chopping the third burger to the server. Once they do this, the participant will click next tick. So that means this time step will elapse because they've made their allocation decisions. And then this other sign will pop up saying that the chef will finish this task in 1 tick, the sous chef will finish this task in 2 ticks, and the server will finish it in 3 ticks. So now they're already getting a signal that, the chef is really good at chopping and the server not so much, and the sous chef is kind of in the middle. So they can learn over time in this simple environment about how to perform better. So in this way, we're trying to mimic how an actual worker in a real environment will actually learn over time, like what is the right sequence of decisions to make. But hopefully using AI here will actually help them speed up that learning curve. Okay, so now that I've kind of introduced the game, I want to go back to kind of what the problem formulation is and how we actually extract these tips from a machine learning framework. So keeping in practice with a lot of those previous examples I mentioned, we're thinking about complex environments where people need to make sequences of good decisions in order to actually have an optimal policy. So like in the emergency department, ordering labs in advance means that you're trying to avoid a bottleneck. So you're trying to be forward looking. Similarly, if you're a driver, you might do similar actions. So it's kind of natural for us to embed this in a kind of Markov decision process framework. So we'll be thinking about an optimal policy versus the human trainee who is executing a suboptimal policy. So here we see a little diagram. So everyone starts off in the same state. The optimal policy will take an action, observe a reward, transition to a new state, and so on until they get to the goal. That's their standard MDP setting. And they're executing some policy pi star. In contrast, the trainee is going to execute some probably suboptimal policy pi. So they'll probably transition to different states that we haven't seen under the optimal policy and get a different set of rewards. But importantly, we should note that just because you might want to take actions right now that have low reward, if it helps you transition to a better state later on, that will have higher reward. So for example, if I were myopic, I will immediately assign every worker some tasks so that they're not dawdling. But if I'm trying to look ahead, I might think, look, the server like really shouldn't be chopping because he's really bad at it. If I just wait one tick, I can assign him to plating, which he's much better at. So in that case, I'm actually losing some reward because I'm letting this worker idle, which is a waste of time. But then I'll transition to a new state where I'm able to make a much better allocation decision. And this is exactly the kind of forward-looking task that can be difficult for humans, especially when there are disruptions and so on. Okay, great. So now the first thing that we need to do is try to figure out what the trainee's policy is. So we know what the optimal policy is. And this we're trying to do from trace data that we've collected from this agent who's actually executing actions in the state space. So like if I have a driver or a physician, then I can see what in machine learning, they call rollouts, which are basically sequences of state action reward tuples. So I see that they were in a particular state, they took this action, they got this immediate reward, and then they moved to a different state. And I see lots and lots of these kinds of rollouts. And now from this, I want to, this can be very noisy because humans aren't, perfect deterministic policies. There's a lot of noise into how they actually behave. Given the same exact environment, they may behave differently at different times, right? So we want to actually use machine learning to try to figure out what policy they're executing so that we can give them a good tip. And the tip is going to be of the form because we want them to be interpretable and easy for them to incorporate into their workflow. We're going to restrict the tips of the form if this particular state, then do this. Right? So how do we do this? The first step, like I said, is that we have to learn the trainee's policy. So we have the optimal policy, we have the trainee trace data. We want to infer the trainee's policy. And one popular way of doing this in the machine learning literature is to use something called imitation learning. So it tries to imitate the human in order to learn a policy of what they're doing. So why is imitation learning hard? If you look at a bunch of data that you've collected, this is the trace data of what this particular trainee has done. Unfortunately, you only see what they actually did on distribution. Whereas if you were to actually simulate counterfactuals, like if let's say that I fit a model of what policy they're executing, I might actually, because of the randomness in the Markov decision process and the state transitions, go off distribution. And once I go off distribution, I now have no idea what this worker would actually do because I haven't seen it in the data before. And so I might start predicting things that aren't actually reflective of what the human does and then end up in a completely different part of the state space that the human would have never gone to. So this is the typical challenge with imitation learning. And the way that kind of these state-of-the-art machine learning techniques have addressed this issue is to regularize any sample paths towards sample paths that have been seen in the data. So you don't want to get too many counterfactual paths that are totally different from what you actually saw in the data that you collected. And this actually worked very well for us. So we just kind of used this off-the-shelf technique to learn these policies by the trainee. So usually in Markov decision processes, people think about learning the value function. In machine learning, people have found that learning the Q function is much better. So this basically tries to predict the reward of the policy at a particular state for a given action. And I'm not going to get into details of that, but basically that's what we use we use basically supervised learning to predict this Q function, and that will help us reconstruct the policy of the human. So now we have the trainee's policy. And so we have pi star. We want to figure out what is a good tip, an interpretable tip that we can offer that will bring the reward of pi as close to the reward of pi star as possible. And again, these tips will take the form of if then else rules. So a tip here is just going to be, like I said, it's a state constraint and an action tuple. So if you're in a particular state in this kitchen, what kind of action should I tell you to take instead of what you were doing already? So the goal here is that we want to look at the value function or kind of the overall reward of using the human's policy plus the tip and the difference of that compared to using just the human policy. So there's a very important assumption here that the human is going to perfectly comply with this tip and everything else will be conducted exactly the same as they would have had they not received the tip.
I have a question to you here. Can I ask you a question?
Of course, sorry, go ahead.
Yeah, this is very interesting. Just out of curiosity, when you run the experiments, do the players know at every point in time how many points they accumulated or where they are?
They do. So they're told beforehand. So the rewards are very simple. It's just a multiplier of the number of burgers that they compute. And they need to complete 4 burgers and they need to finish it in a certain number of ticks. And they're clicking the next tick button so they know how many ticks there are. And we're also tell them beforehand, what is the optimal number of ticks where they would make, you know, kind of this big bonus? What are the different tiers below that for which they would get different rewards? So it's full knowledge.
So they have a roadmap at every step of the way.
They do. They just don't know what is the right sequencing of decisions.
Sure.
Get it. Yeah, exactly.
Okay. Thank you. This was very useful. Yeah.
And yes, feel free to interrupt me with any questions. Right. So our goal is to find one of, so there are many if then else tips. We can actually enumerate them, but our goal is to try to figure out what is the tip that will maximize the reward difference, bring them as close to the optimal policy as possible relative to where they are starting from. And again, like a strong assumption we're making here is that they will perfectly comply with it. As I'll show in the experiments, that's not true. And often there's both positive and negative spillovers that come in here. But for the tip inference algorithm, this seems like as reasonable as any other way to choose a tip. Right? So this actually turns out to be a very computationally difficult thing to compute, just because a tip actually changes the state distribution that human ends up in. And so we need to actually consider the fact that from then on, their value function might completely change. So we come up with this new approximation for figuring out for ranking these tips based on how likely they are to improve the reward and how much they are going to improve the reward. And we use this to kind of pick the best tip. Okay, so now that we did all this, we now have a way of actually going from collecting trace data from the human user all the way to picking out a good tip. So we want to actually move on to doing a user study where we will actually present that tip to the trainee. So that's all I'll say about the algorithm unless there are any questions, and I'll move on to the behavioral study again. Okay. So the study will have to proceed in 2 phases. So in the first phase, we're just going to let people play the game because we need to gather trace data so that we can actually infer their policy and find good tips. So the first phase for our studies will generally be pretty small. We're enrolling about 150 to 200 people in there to try to figure out what are reasonable tips to offer them. And then there's a second phase where we actually evaluate the tips. So we'll evaluate both our tip as well as a couple other baselines that I'll mention in a second. And this is sort of the larger study where we'll have like 1,000+ Mechanical Turk participants. They're all playing this game and they're all offered different tips based on what arm they're in. So all of these studies are pre-registered, and we consider 2 different variants. So the first variant is less interesting, so I won't spend as much time on it. It's the static configuration. So you have a static environment, and people are going to be playing in this. We'll give them the tip, and then you'll see that it's kind of an easy task. So everyone kind of learns naturally on their own. With the tip, they learn faster. The second setting is more interesting. So this is kind of trying to mimic this disruptions based on new technologies or people or new environments. So here what we'll have is that they'll start off playing the original system. And then the chef, one of the workers, will leave on vacation. So now they have to manage the same orders, but with just 2 workers. So they need to unlearn the old policy that they were playing before and actually try to execute a new policy. And this is obviously much more challenging for people to do. And here's where we really see that tips can really speed up learning and help them discover new strategies. But I'll kind of overview both sets of results. And just to quickly speak about the different arms, and this will be the same for both studies. First of all, we have a control arm that offers no tip, so that's not very interesting. Then we have our algorithm, which will offer our tip. Next, we'll have a human tip. So here, after we run the phase 1 study, we actually ask people, now that they've played several rounds of the same game, if there's a newbie who's coming in to play the game, what kind of a tip would they offer? And we just choose the most frequent one. We have a predefined list that includes all our if then else rules, and then also a couple other tips that they can write in that are maybe more interesting or more relevant according to them. And then finally, we have a simple count-based frequency, count-based baseline. So one of the things that I mentioned before is that this trace data is difficult to kind of make any sense of without trying to estimate these value functions and these policies. One thing that you could do that's pretty naive is just look at how often certain state action pairs differ between the optimal policy and the human. This is not actually a great policy because it doesn't account for whether that state action pair matters to the ultimate reward and the value function. But it's kind of the most, it's kind of the simplest thing that you can do if you had a bunch of trace data. So we'll also add that as an arm just to see how it performs. Okay, so the first study, the static study, is very simple. Again, they have to make 4 burgers within 50 ticks. They have these 3 workers. And they're just going to play this game 3 times. So it's exactly an identical game. They'll just start over, they do round 1, they complete it, they do round 2, and then they complete it, and they do the same game in round 3. And when we infer these tips, so again, we have about 183 people in phase 1 where they're just playing it. When we infer tips, we get something like the state here is going to include the order number, like which burger they're thinking about, the subtask, like whether it's chopping or, plating. And then the virtual worker we're thinking about assigning it to, whether it's the chef, the sous chef, or the server. And then the action is assigning some order subtask pair to a particular worker. So this is the kind of tip that our algorithm gives. As you can see, it's not particularly readable for a human. So we're going to make some simplifications here. So if we get, often what we end up getting is because there's a lot of symmetry in the state space, we'll end up getting that for burger 1, assign the chef cooking burger 1, and for burger 2, assign the chef cooking burger 2, right? So in this case, clearly that just means assign the cooking to the chef twice. And when we actually offer it to the human participant based on pilot studies, it seems like it would be most clear to the human worker if we said something like chef should cook twice, right? So there is some loss of information here. This state action pair that I originally presented was kind of much more informative because it's saying specifically burger 1 and burger 2, whereas here it just says chef should cook twice, which means that the human now needs to try to make a leap here and figure out how this would actually incorporate into their workflow. And this produces some interesting dynamics, but this is much more readable and understandable to them.
The question is, Hamza, sorry, we participants see those algorithmic suggestions and there's the natural aversion. I don't understand this black box. So how do you go around it?
So we don't actually tell them if the tip is from the algorithm or from one of the other arms.
Okay.
So they will, there's still some natural algorithmic aversion that I'll mention towards the end, which is that the algorithm's tips can be much more aggressive than the human's tips. Human tips are generally more regularized towards their own policy just naturally. And that creates some aversion. But in this case, part of the reason we are making this more aligned with what a human would say is to reduce algorithm aversion. So something like this, so like on top, is something that we found in pilot studies that people just didn't respond to because it's almost read like machine language.
And do they respond to it on the next round, or it takes them a while to get into this rule?
They actually respond almost immediately, but it depends on the setting. So yeah, I'll show you that in a second.
Okay.
Yeah, that's a great question. Okay, so the inferred tips in this case, so in the static setting, again, this is a very simple one, is just that the chef shouldn't plate. So like I showed you the statistics before, chef is really good at cooking, which is kind of the difficult bottleneck task, and they're bad at plating, the server is great at plating, so it kind of makes sense that that's the tip. What the human users after phase 1 picked as the most frequent tip is that one should strategically leave some workers idle. And this kind of makes sense because usually when they play the first round, they never want to leave workers idle because that seems like a bad idea. But by the time they get to the third round, they learn that, you know, it's better to leave that server idle and wait to give them the plating task than to assign them a cooking task and have them take up this whole time and be the bottleneck, which is cool that they learned that on their own. And then the baseline, like I said, is just we're going to look at the state action pair frequencies. So again, the issue with this is it doesn't account for the reward structure. And this basically says that the chef should chop only once, which is true of the optimal policy, but maybe not as helpful as kind of the other points that were made. So what happens is that we basically, these are the 4 arms. When we run phase 2, for all of the rounds in phase 2, there will be a tip that shows up at the top of the game. And depending on which arm participant randomly gets assigned to, they get to see that for the entire game. So these are some of the results. So first of all, this is the control arm. We're plotting the number of rounds, the 3 rounds, and the ticks to completion. And you see that they start off at about 26 ticks, but over time they improve. So, and this is with 1,300 participants split equally between the 4 arms. So clearly people naturally learn over time, which is kind of hopefully what we were expecting to see. And then if we actually look at the other arms, we see that the baseline tip and the human tip really don't make much of a difference because people naturally learn in this case that you should leave people strategically idle over time. So that's not really that useful to helping them improve performance. It's not that prescriptive. This is actually different when I'll show you the disrupted case. There, the human tip is actually much more useful, but in this case, it wasn't. And the baseline tip didn't really make a dent because in this case, the sous chef was always kind of chopping once anyway, and it doesn't really help with that. That's not the bottleneck task. The bottleneck task is cooking versus plating. So assigning who to chop is not really kind of going to impact the value function, which is exactly the issue of just looking at frequencies. So this is average performance. One can think about who gets optimal performance. So the optimal policy will finish these burgers in 20 ticks. This is very doable. All the co-authors did it. So it's not a particularly difficult task, but you see a lot of people on average, even on the algorithm arm, they're still doing about 22.5 ticks. So we can look at the percentage of Mechanical Turk participants who hit optimal. And we see that a decent chunk of them, again, this is a static setting, so it's kind of easy. A good chunk of them are actually able to hit the optimal performance. And you see that the algorithmic tip kind of helps push them in that direction. So again, I think the really interesting setting is a disrupted case. So this is the case where, you know, we have a new technology or the environment changes. So you've gotten accustomed to a particular policy, and now you have to change gears to take a different route or a different policy. And this makes things, this is somehow harder for humans to grasp. So here again, just to remind you of the setting, we have 2 rounds where we have all 3 workers. So here we tell them the chef should never plate so that they quickly learn how to adapt to this setting. And then we tell them, unfortunately, the chef is on vacation, which is a little bit strange given that it's a pandemic, so no one's really traveling. So now they're left with just the 2 workers, the sous chef and the server, and then they play 4 rounds of this game. So we'll be looking post-disruption how their performance changes from round 3 to round 6, depending on what tip they get. So again, we first do a phase 1 study on about 172 participants just to get some trace data to infer some tips. So here the algorithm says after the disruption, the server should cook twice. So note that this is a sharp departure from what we did before. Before we said the server should never cook. He sucks at cooking. He should just focus on plating. But now that the chef is gone, the server needs to pick up some of the slack and needs to actually cook. The human policy, interestingly, says the server should cook once. This is what the humans are actually recommending workers do after doing phase 1. So they've completed 4 rounds of this disrupted setting. And I thought this was really interesting because this is actually the wrong tip. The optimal policy says the server should cook twice, but in some sense, it makes a lot of sense because it captures the same kind of dynamic that we need to pass more of the cooking tasks onto the server. And about a quarter of the participants recommended this particular tip, so it's very popular. The baseline tip says the sous chef should plate twice. So again, we see this count frequency thing, like it never really seems to touch on the actual bottleneck, which is an issue with just looking at frequencies. So again, we'll put them into 4 different arms in phase 2 and offer them different tips once they get to the disruption. And what we see, so now we have 1,000 participants across all 4 arms. The number of ticks to completion has gone up a lot. That's because we now only have 2 workers. So naturally, this task is just going to take longer because we have the same number of burgers, but we have fewer workers. And again, we see that people naturally learn over time, right? So even in the control arm, the amount of time is decreasing. And then we see, we can throw in the other baselines. So we see that the baseline tip telling people to plate is just nonsense because the bottleneck here again is cooking. So looking at frequencies is just not a great idea. But the human policy, even though I told you it gave you the wrong tip, it actually does improve performance quite a lot. And it's actually halfway between our algorithm and the optimal policy. And this is because it's still hitting on the right point. So people are very good at figuring out what the issue was and communicating that. And we kind of knew that because from the OB literature, right? But unfortunately, it's still the wrong tip. And we see that with the algorithm, we can do much better. And you really see this when you start looking at the number of people who hit optimal. So optimal here is 34 ticks. If you sequence your actions correctly, you can finish this task in 34 ticks. And we see that basically nobody in any of the arms gets optimal except the people who get the algorithmic tip. So this is a huge difference. For the human baseline, it kind of makes sense because again, their tip is wrong. Like if you can't hit optimal if you have the server only cooked once, and people just don't figure it out because it's actually quite challenging. But then you give them a little nudge, you give them a hint that, hey, the server should be cooking twice, and they're actually remarkably good at figuring that out. And they actually learn linearly over time. So we see that by combining their own learning and this tip, they're actually able to make a lot of progress. And I think this is really where the power of using AI or machine learning in on trace data lies. They can really complement their own learning with a little bit of a nudge. So I wanted to mention a couple things that are happening under the hood here.
Hamza,
yeah.
Can you go back to the previous slide, please?
Yeah.
Okay, here on the algorithmic learning over time. So basically, is it they're building more trust of the algorithm, or is it because they just see it's working and the trust?
That's a fantastic question. Yeah. So interestingly, the compliance for the algorithm arm is actually lower than the compliance for the human arm because it's such an aggressive shift from what they were doing before. But they're actually able to incorporate that over time, and they learn how to. But once they assign the server cooking twice, they need to figure out what to be doing with the other worker, how to adjust the rest of their policy in order to accommodate that tip. And we actually see that the successful ones, like the people who are actually hitting optimal, they're able to learn other tips that we didn't even offer them that are part of the optimal policy in order to accommodate that. So there's kind of positive and negative spillovers that are happening here. Wow. I'll show that in 2 slides, which I thought was really cool and like potentially a direction for future.
It is, yeah.
Yeah. Yeah, so people are very interesting. So first of all, the baseline here. So there's an issue on focus. Why the baseline doesn't work is because the algorithm and the human tip, you know, for making a burger, you need to chop the meat, cook the burger, and then plate. The algorithm and the humans kind of know that the bottleneck is here in the middle, right? Whereas if you're just looking at counts or frequencies, you're looking at the end. By the time you get to the end, there's really no opportunity for you to improve your performance and substantially improve your reward. And this is why it's so important to kind of look at the original value function and look at the actual policies that are being executed than just looking at frequencies, which I thought was like a big argument for why using machine learning is more useful than just kind of trying to get some simple summary statistics off of the trace data. The real challenge for humans here, and the reason the algorithm is kind of even more interesting here than in the static configuration, is that humans need to unlearn their old strategy. So in the previous strategy, we told them server should never cook, right? Like when there are 3 workers, the server should not cook. And now they need to figure out that the server does need to cook. And the human policy is much closer to server shouldn't cook, because they're saying, okay, let's change it a little bit. Server should cook once. The algorithm is very aggressive because they're saying the server should cook twice, which feels wrong. And that creates some kind of aversion to the tip because people feel like that tip is not correct because it's just so far of a shift, right? And so if we look at compliance, right? So this compliance on the y-axis is measured with respect to whatever tip they were offered. We see that the compliance to the human tip is actually more than 80%. So that's really high compared to the algorithm, which is only about half of that, even towards the end. So they do comply over time, to Avi's question. The compliance is increasing, but it's substantially less than the human tip because it's so aggressive. So I don't think that this is specifically because it's an algorithm, but it's because, you know, it's not respecting what they had learned before, even though what they had learned before is wrong. Right? So that creates some interesting questions about how one should be thinking about these tips, designing them. Maybe we should regularize them towards their older policy and make small steps. But the other thing that happens here is that there's also a positive spillover in that the reason that people in the algorithm arm are able to hit optimal and the people in the human arm are not able to hit optimal is because there's a positive spillover that they discover other strategies. So we told them that they should cook twice and they should, for the server, and cook twice for the sous chef. The optimal policy also involves the sous chef chopping 3 times and the server chopping 1. We told them about the split for cooking. We never told them about the split for chopping. But we actually find that in the algorithm arm, people learn based on what the split is for cooking, what the split should be for chopping, even though that's not something we gave them any information or nudge on. Wow. So this is the compliance for that other tip that we gave them no information on. We see in all the other arms, no, they don't learn that strategy. But in the algorithm arm, they learned this strategy, even though it's not something we told them. So that's the other side. So there's negative spillovers from lack of compliance. There's positive spillovers from enabling them to learn new strategies, which is what humans are great at. And I think this kind of creates a lot of interesting dynamics in how we should actually be thinking about picking the right tip, because we want to maximize this type of spillover and we want to minimize the previous spillover.
Hamza,
yeah.
When you show compliance, how do you measure compliance with the tips, and how often do you show the tips?
The tip is shown at the top of as a banner the entire experiment. Okay. So that's always there for their reference. Compliance is measured with respect to the actual action that they're taking. So here we're looking at the fraction of people who assign sous chef chopping 3 times and server chopping once within the entire round. Mm-hmm. Okay. And similarly, in the previous one, it's a little bit more complicated because for the green line, we're thinking because the tip was assigning cooking once, we're looking at how many people assigned cooking once. For the red one, we're looking at how many people assigned cooking twice because that was the tip. So it varies. It's compliance to that specific tip.
Okay.
Cool. So I think that's pretty much all I have. So a couple other steps that we're thinking about is now, taking this out of the lab experiment setting and trying to test it with real data, like for driving or something like that. We're actually also really interested in thinking about this for teams because that's a very common source of disruption. So here, like the chef leaving, it's very common for people to be matched to new teams, say in EMTs. And that actually changes how we offer tips because then there will be spillovers on other people's performance. So we need to think about it as a joint or holistic system. And I think there's a lot of interesting nuance here about understanding how to combat this algorithm aversion or improve compliance while still enabling them to learn new strategies. Thank you.
Thank you. Fantastic talk. I want to ask you something here. Mm-hmm. You talk about providing the tips, okay?
Yeah.
Those tips from organizational perspective in the business world don't come for free.
Right.
So what do you think might be, from implementation perspective, the tangible as well as the intangible costs of tips interpretability? How far should we go in terms of interpretability as we deliver tips to the staff?
Yeah, I think that's really interesting because the more interpretable the tip is, the more constrained it is in terms of actually being able to improve reward performance and being able to give them a concrete way in which to improve. But on the other hand, if it's not interpretable, they don't absorb the tip. And they're not able to do this thing where they're able to easily integrate it in their workflow in a flexible way and find these new strategies. So I think ideally it would just be a dynamic setting. So whenever we give them an interpretable tip, they actually change their policy, and then we'll try to estimate the new policy and offer them a new tip. It has to be an iterative dynamic process. And I think that will minimize the cost of the tip being interpretable because that restricts your action space, if you will. I think this shows up a lot in kind of like year-end peer reports where people try to give you meaningful feedback on how you can actually improve performance. But they're not necessarily looking at what kind of code you pushed or what kind of actual work that you did. And looking at that granular data and personalizing it towards you, I think can actually help compliance a lot.
Yeah. I'm not sure, why did you mention that making the tips more interpretable makes it more difficult for the users to adopt them?
So in this case, so the original tip was kind of that our algorithm will pick up is it'll say like at tick 22, assign cooking of burger 3 to this worker. So that's kind of much more easy to implement in the sense that it tells you exactly what you have to do. Whereas if I just tell you, hey, make the chef cook twice, that's a little bit harder because you have to figure out when, which burger, and so on. But people respond much better to the second thing than the first thing. And it's also much more flexible because the first thing might not even make sense for their workflow or that particular set of conditions that they're facing. So you need it to be high level enough that it's useful, but not too high level that, you know, it's not, yeah, there's a tension between implementability for them and usefulness, if that makes sense.
I got a question from one of our participants. Under what general conditions, what settings, the algorithmic tip will be the most or the least useful?
Most or the least useful?
Yeah.
I think when compliance is really low, the algorithmic tip is not useful. But in general, if most people are compliant and they're able to leverage the tip in an appropriate way, then the algorithm by definition will probably give you the best tip. Another issue might be that the optimal policy that you're estimating might be on stale data. So for instance, if the trace data that you collected is prior to the disruption that happened and your algorithm is not aware that a disruption has happened, that could create issues. So as long as you're dynamically collecting new trace data, and you're updating your policy, as long as there's no compliance issues, I think the algorithm tip is usually better, or that's what we saw in this case.
Now, when you implement the tips, are you also collecting trace data, or are you just using historical trace data before you implemented the algorithmic AI? You understand
we're using, that's a great question. We're using the trace data that was collected from historical, like the phase 1. Just because of sample size issues, we weren't able to get the same workers to come back for phase 2 after we compute the tip. So that's just a limitation of, you know, doing it on Amazon Mechanical Turk. Ideally, in practice, if this were implemented, like we would systematically be consistently collecting trace data and offering new tips. So that's absolutely on the nose. Yeah.
Yeah. Another question that came, which is also very interesting, kind of. What are the business contexts this framework will apply to?
I think that's a great question. I think it's useful for things like bargaining, for example. Like there have been studies that are applying like deep reinforcement learning on like how people bargain on eBay, because then you see a lot of trace data. Things like the gig economy, or I think like healthcare context, where a lot of healthcare context in the sense of like when you order labs or when you take new patients or patient routing type of decisions that are it basically has to be a setting where there's a lot of trace data. It's very granular and you're not too worried about kind of unobserved factors. So I think these kinds of settings kind of fit that pretty well.
Did you find any relationship in the experiments between the performance of a particular individual and how the tips were useful for them in the first phase, in phase one?
Phase one, we don't offer any tips. That's a great question. But in phase one, we just let them play the game so that we can collect data to infer the tips. And then in phase two, we offer tips. We did try collecting some other information, like how often they've played games, like what their college education was and things like that. We didn't see anything that was too surprising on that front.
I have a question.
Yeah.
Thinking about it, the setting you put is fairly stationary. What would happen if people want like vegan hamburger or cheeseburger or regular burger, or demand is not stationary, but kind of fluctuating the way it happens in real life?
Right.
Instead of just 4 hamburgers, either 6 or 20 or something like that, kind of adding a little bit noise into the system.
Yeah, I would love to study that. That's what we originally wanted to do. So I think here the challenge is that the Mechanical Turk workers are only playing for a short amount of time. So I think in practice, that's actually exactly the kind of setting where I think this kind of framework would be even more useful, because there's so much more noise and it's so much harder to get any kind of useful insight. But this is a very short time frame. So we just found that they couldn't, if the task is too difficult, there's too much noise and too many things are changing. And then they also have to think about incorporating tips. It was just a little challenging in a short time frame. But I think, yeah, when there's a lot of noise, maybe demand distributions depend on time of day and things like that. That's really when machine learning will be extra useful, I think.
And do you feel that when you run the experiments, participants kind of were bifurcated? Some of them say, I don't really trust the algorithm, or others says, if this algorithm, I take it as my orders, marching orders, and I don't think twice about it, and throwing away the intuition?
I think compliance was relatively bimodal, at least in the disrupted case. There are a bunch of people who completely complied with it and a bunch of people who didn't comply with it. And that's why we look at the people who hit the optimal performance, because the people who comply are usually the people who can end up getting to the optimal performance. I can't speak to this. Park did look at all the user feedback and read their comments. And sometimes they would say things like, I don't trust this tip. It doesn't really make any sense. And I think that's more of a challenge of them trying to figure out, like, this is my current workflow. How can this tip possibly fit in? So some people just struggled, for example, to get cooking twice into their policy, given that their policy they're executing is so different. So I don't think it's necessarily algorithmic aversion so much as telling people to do something that's just so far from what they're currently doing will create aversion. And I think that's a very human response.
Yeah, we like to kind of get the intuition. On
Right.
the other hand, physicians use Tylenol, and most of them, you push them, they have no idea how Tylenol works, but they prescribe it or give it away. And you can understand the example yourself. Right. I have a general question to you. I know some of your work, and I'm a very good believer in the quality of your work. I enjoy reading all your papers. And I want to ask you this. Most of your work has been more kind of theoretical and analytic. So how does it feel going into behavioral empirical work? What did you learn about it, about yourself and about the field?
I learned that there's a lot that I don't know. Yeah, I mean, it's been, this project probably took a lot longer than it would have taken a behavioral person, I'm guessing. But it was really helpful to have Park, who's been doing a lot of behavioral empirical work in operations, to kind of help us with figuring out how this is done. I think it's quite challenging when people are thinking about designing these sorts of experiments, because unlike theory, like with theory, like you kind of know what to expect when you're going, like by the time you formulate the problem, you kind of already know what your results are going to be and what assumptions you'll need. Whereas here, it's a big learning process. Like even designing this game, we started off with a much more complicated game that was more like what you said, where people would get many different orders. They would get tacos and pasta and burgers. And then we learned that, that's just not feasible for a Mechanical Turk worker to play with. Then we tried different kinds of tips. We started off with these kind of more complicated tips. Then we learned that, it needs to be more small and digestible. So it's actually a lot of fun, because there's a lot more that you can learn about people fundamentally when you're doing this kind of work. Whereas I think when you're doing theory, you get out of it exactly what you think you're going to get out of it.
That's how much do you pay mechanical techs if they do a lousy job or if they do an outstanding job? If I may ask.
We have some strong rules about that for fair pay and stuff. I believe it takes them about 15 minutes to finish this, or 30 minutes, a little bit longer in the disrupted case. I think they get like maybe something like minimum wage, like $3 or $4 if they actually finish it, if they do the worst possible. So they actually take the entire time, they dawdle and they don't do anything. And then they get about $1 to $2 more if they actually get pretty good. And then if they hit optimal, then they get kind of a pretty large bonus. Unfortunately, that doesn't happen that frequently, but I think they can get up to $5 or something like that.
Additional $5, okay.
Yeah. But that's not expensive for us because not that many people.
No, that's very interesting in its own right. Yeah, definitely. And basically what I find very exciting about the research is the fact that the business world is changing very rapidly, and the need to train and retrain individuals in every facet of life. You use medical example and surgeons, but everybody needs to be learning. And what we teach today to business school students is not what we were teaching 20 years ago or 15 years ago.
Right.
And sometimes my students tell me, well, Professor Seidman, you know, what you teach us, because I teach in the information system side of business, it will be outdated in a few years. I tell them, look, if you want something stationary, go study religion or philosophy, okay? But then you won't make much money out of it, okay? But any other field that makes money, whether it's accounting or finance or operation or IS, you need to constantly learn. So we can give you the state of the art, but you have to keep updating yourself as time goes by, you know? Otherwise, the half-life is shorter. And what we like to do is kind of teach you how to think, and this is very important. And I think what you have shown us here is really fantastic. And where does the paper stand, may I ask?
We're still writing the final draft, so we're hoping to submit it soon, knock on wood.
So once it's ready, if you can share it with us, I would greatly appreciate it.
Of course. Yeah, and I agree, the field is changing. I think that's what makes it fun. So, you know, even as professors, we get to keep learning, which is a lot of fun.
No, that's what I like to do the most. So, well, that kind of wraps up our things for today's Boston Digital Business Leadership Live event. And my objective, as always, is to change the way you think. And I hope we succeeded with it today. I want to really thank Professor Hamza Bastani for joining us today from the Wharton Business School. And hopefully next time we can host you for good coffee in Boston as a live event, okay? So we owe you one, okay? But that's the best we can do these days. Hopefully pretty soon we can start traveling more so. And I want to thank you for this outstanding scholarly presentation, which is thought-provoking. And the recording of this event, as well as all our other Insights at Questroom live events, can be found at insights.bu.edu. So thank you very much. And please give all of us a big hand to Professor Bastani. Thank you very much. And I'm very grateful for you taking the time.
Thank you so much for having me.
Fantastic. Yeah. Thank you very much and stay in touch. Bye-bye.